Yesterday, we talked about the product operator formalism. I introduced the mathematics behind it. Essentially, we have a spin density operator defined by A that is with an Hamiltonian developing with an angle phi, and the Hamiltonian is B. But now we want to fill this a little bit. What operators are available? That means essentially which Hamiltonians are there usually that we use. It's very clear. When we look at it, then we have, of course, the chemical shift, the Hamiltonian for the chemical shift. And that's usually written as, for example, omega, and let's call it omega 1 for I1 Z for the spin 1. And when we have two spins, for example, we might have another one, omega 2 for I2Z. And these are circular frequencies, so you can also write it as 2 pi nu 1 I1Z plus 2 pi nu 2 I2Z. So these nus then are real frequencies in hertz, while omega is given in radians. Then you have, of course, other Hamiltonians and the J coupling, Hj, that can be written as 2 pi j I1 times I2 for the two spins. This is the full coupling Hamiltonian. And if you write it out, then this is 2 pi j, and then it is I1x times I2x plus I1y times I2y plus I1z times I2z. And then, of course, when you go to in liquid state, for example, to partially aligned samples, then we also have a dipolar Hamiltonian, which I would like to mention for completeness, dipolar coupling Hamiltonian, and that you would write down as 2 pi j 2 times I1z, I2z minus I1x, I2x minus I1y, I2y. That's the secular dipolar Hamiltonian with which you can describe all coherent effects that come there with residual dipolar couplings in partially aligned samples. But now we want to look at what is the structure of these operators. So we can see, for example, when we look at omega 1 I1. So when we look now at omega 1 I1Z, then this is simply 2 pi nu 1 fourth and the big matrix with 1, 1, minus 1, minus 1, 0 everywhere else. When we look at omega 2 I2Z, then this is 2 pi nu 2 divided by 4, and we have the form 1, minus 1, 1, minus 1, 0, 0. So two diagonal matrices. And when we do the calculation all together for Hj, then we see that this will be 2 pi j divided by 4. And then we have a matrix where we have 1, minus 1, minus 1, 1 in the diagonal. We have 2 here in the center, and the rest is 0. Indeed, it should be a minus here, so we can write it maybe better. Maybe something interesting here for the J coupling. When we look here at the states that are connected with it, then in this row we have alpha alpha, then alpha beta, beta alpha, and beta beta, while on the other side we have here alpha alpha, alpha beta, beta alpha, and beta beta. And so the two transitions here, these two transitions with the two, they kind of represent transitions from alpha beta to beta alpha. And that is what's called flip-flop transitions, especially energy conserving. And they also lead to so-called zero quantum operators. And the characteristic for isotropic mixing or isotropic coupling. This is the structure of the Hamiltonian. And when we look now what we have in real life, then usually we have a combination of couplings and chemical shift. So if we look at the combination, like the whole Hamiltonian, which would be H chemical shift plus Hj, then we end up with an Hamiltonian that looks like this. We have the J coupling, actually pi half, and now I have to be careful because then we have minus nu 1 minus nu 2. We have minus J minus nu 1 plus nu 2. We have minus J plus nu 1 minus nu 2. And we have J plus nu 1 plus nu 2. And the other elements are mainly 0. Just here we have 2J and 2J. And when we look at this Hamiltonian, then we see one thing. We have the frequencies nu1 and nu2 along the diagonal, then also the J coupling. And when the J coupling is on the order of the chemical shift or the offset values nu1 and nu2, then they all interact. However, quite often we have very large chemical shifts on the order of even 1000 Hertz easily, or more than 1000 Hertz, but our J couplings are just on the order of, for example, 10 Hertz. And then something happens, then we can see that these terms here, the two J terms, they can more and more be neglected because nu is much, much larger than J. And we can do this, and when we do this, for nu1 minus nu2 larger than J, then the Hamiltonian will be just J minus nu1 minus nu2 minus J minus nu1 plus nu2 minus J plus nu1 minus nu2 J plus nu1 plus nu2, and all the rest would be set to 0. We have a diagonal Hamiltonian, and this is simply the H chemical shift plus Hj, let's say weak, the so-called weak coupling limit. And then we also can derive from that simply that Hj weak would be 2 pi J I1Z I2Z. Yes, of course. So we have all this, and the weak coupling Hamiltonian is indeed something that we always use, for example, in the heteronuclear case, because if we have two heteronuclei like a proton and carbon, then the chemical shift difference is many megahertz, and that really is very large compared to the J coupling, and we completely neglect about the J coupling. And what is it like physically when you look at it? It's like you have two spins, for example, spin 1 and spin 2. They're both coupled, and now they have no offset. Then they rotate around this axis, which does not matter. But also when they are here and have both the same frequency, they will rotate the same way. Yeah? So now we have a chemical shift difference. And to make it easier for me, I say one spin has the frequency 0. That means the x-axis stays. Yeah? While the other spin, the second one, has an offset. When it has an offset, it will rotate. And now simply think of a term I1x times I2x. Now it's I1x times I2x. A few moments later, it's I1x times I1, I2y. A little later, it's 1x times minus I2x. So it's all together, it's minus. Then also I1x, I2y times minus 1. So what we have is, I'm just looking now at this. We have plus I1x, I2x minus, plus, minus, plus, minus. It's clear, if this rotation is fast enough, we average out simply the x component. The same is true if we have both in y. Yeah, one is standing still, the other one is rotating, and also the y component will average out. Just zz, we have no rotation there, so it remains always. So as long as the chemical shift difference is large enough, we always have just the zz component that is being active, while the xx and yy component get more and more negligible. But of course, when they both have the same chemical shift, if we have isochronous spins, then the isotropic Hamiltonian is fully active. And when we are in the intermediate range, where we have a very small chemical shift difference and a slow evolution here of the second spin, then we end up in artifacts that are called second order artifacts, or you may know from the Roof effect. Yeah, and this can also be seen here mathematically. As I said, this is simply this 2J that relative to the chemical shifts, nu1 and nu2 gets smaller and smaller and smaller. So we have now these operators, but just for completeness, I should also mention we have another Hamiltonian that we can control. It's an important Hamiltonian, the radio frequency, and when I irradiate along x, then this is simply also minus and omega RF Ix, for example. And for two spins, it's actually I1x plus I2x. And when we look at the general case, then HRF is minus omega RF times cosine phi I1x plus I2x plus sine phi I1y plus I2y, where phi is the pulse phase. So a pulse phase of 0 is usually connected with an x pulse, and a phase of 90 degrees with a y pulse. So far, we only looked at the product operator formalism if we have a single Cartesian product operator component active in the Hamiltonian as well as in the spin density operator. Now, what happens if we add up a second component? As we have seen, we have at least two components in the Hamiltonian, probably even many more. More than one product operator. Then we have the first case that our density operator rho 0 actually consists of more than one product operator. So let's call it a linear combination of two, A1 plus A2, meaning we have two operators, capital A1 and capital A2. And now if we calculate rho of t, then this is e to the minus IHT, and then we have A1 plus A2 times e to the IHT. And there, simple from basic mathematics, it directly follows that we have A1 times e to the minus IHT, A1 e to the IHT, plus A2 times e to the minus IHT, A2 e to the IHT. So it is absolutely no problem if we have a combination of different product operators in the spin density matrix. We simply do the linear combination and we look at each of the Cartesian components separately. So this is very nice. It will work there very easily. But now, how is it with the Hamiltonian? So our Hamiltonian may be omega 1 times B1 plus omega 2 times B2. Then H times T, of course, will be omega 1 T B1 plus omega 2 T B2, being phi 1 B1 plus phi 2 B2, just to deduce the flip angle. And when we then look at rho of t, actually look at rho of 0, how it is evolving under the ht, then we can write down this is e to the minus, and then it's I phi 1 b1 plus phi 2 b2 rho of 0 and e to the minus I plus I phi 1 b1 plus phi 2 b2. And this can be rewritten, of course, here to e to the minus I phi 1 b1, e to the minus I phi 2 b2, rho 0, and e to the I phi 1 b1, e to the I phi 2 b2. So what we actually want to have is that we can apply phi 1 b1 first, and then we apply phi 2 b2. So what you would like to have is we apply e to the minus I phi 1 b1 rho 0, e to the I phi 1 b1, have that first applied, and when we applied that, then we would like to apply the second e to the minus I phi 2 b2, e to the I phi 2 b2. What's necessary for this to be active is actually that these two operators change position. And now there comes a strong limitation of the product operator formalism. This can only be done if only possible if we have the commutator of B1 with B2 equals 0. As soon as the commutator is non-zero, then we have a problem. Then it is not working anymore. So we can state can be used one after each other as long as they commute. If you have two non-commuting operators, then we have a problem. We cannot apply the product operator formalism. Then we have to calculate using the full spin density operator formalism as it was derived already. So, are there examples? When we look at the operators that we have active in NMR, then certainly H chemical shift and the J coupling in the weak coupling case, which is the commutator of, let's say, minus omega IZ with, or 1 I1Z, for example, with 2 pi J I1Z I2Z. Then the commutator, both point along Z, it's clear, is 0. Yes, we can compare them. But if we look, for example, at H chemical shift and the radio frequency along X, then this would be minus omega 1 I1Z and minus omega RF I1X. And we all know this is not 0. This is actually minus I omega 1 times omega RF I1Y. So already in this simple case, we cannot apply the product operator formalism anymore. And when you see calculations, you will always see if there is a delay, You have evolving chemical shifts and the weakly coupled spin systems. But when you apply a pulse, you always only consider the radio frequency field, meaning the RF Hamiltonian, and not the chemical shift Hamiltonian, and also not the J coupling Hamiltonian. These are the limitations, so they're always only approximately valid. And of course, when we look at the full isotropic coupling Hamiltonian, then things get even more complicated. Then we cannot even apply the chemical shift operator simultaneously to the full coupling Hamiltonian. But to show you one example where I think one can learn a little bit, I would like to do one little calculation with you that is not so often done in normal spectroscopy, but I think you can learn fundamental things. And that is when we consider full isotropic J coupling between two coupled spins. In this case, we have Hj, so 2 pi j I1 times I2, and I wrote down already that's 2 pi j I1x I2x plus I1y I2y plus I1z I2z. And this is now 3 Hamiltonian components, xx, yy, and zz. And it turns out that they all commute. So I1x, I2x, I1y, I2y is 0, as well as the others. All commute. So we can now simply calculate this by applying one after the other, one individual term after the other. Let's say we have a starting magnetization. Let's say we start with I1x, and we now apply first 2 pi j I1x I2x times t. Then this is clear. I1x with I1x I2x commute. They are all pointing in the same direction, at least for spin 1. So we end up with I1x. Nothing will happen. Now I make it simple for me. We continue with 2 pi j I1z I2z times t. And this is simply I1x cosine pi jt plus 2 I1y I2z sine pi jt. And then we have to apply the third component, 2 pi j I1y I2y t. Then we have again I1x. This time it's cosine pi jt times cosine pi jt, that is cosine squared pi jt. And then with this we end up with minus I1z I2y, and it's still cosine pi jt from the original one times sine pi jt. Then we have the 2I1y I2z sine pi jt, which is now multiplied with the cosine pi jt. And when we evolve this, then we end up with I2x sine squared pi jt. So something remarkable happens here. We start with in-phase magnetization, and we end up with in-phase magnetization on the second spin. And that is something very interesting, because if we look at a normal weak coupling evolution, then this would correspond actually, this is the weak coupling evolution. This is kind of a subset here. And there we only go to antiphase terms and return to the in-phase term on spin 1. we never develop anything that could be detected on spin 2. We need to apply pulses to do an experiment like COSY. But in the case here of full isotropic or strong coupling, we directly go from one spin to the other spin, from in phase to in phase. And that's actually something that we use in the TOXI experiment, where we artificially make it that all chemical shifts collapse. And then you have automatically this strong coupling. And when you have in phase from spin 1 to spin 2, and you have a coupling to the spin 3 and 4 and 5, then there's nothing that prevents you from transferring further to these spins. You have then transfer from spin 1 to spin 2 to spin 3 to spin 4 to spin 5, as long as you are in this strong coupling limit in this isotropic Hamiltonian. I forgot the 2, normalization. And now I would like you to also look what happens if we start with spin I2x and do the 2 pi j I1 times I2. And that's clear. We just need to replace the indices. So we have here I2x cosine squared pi jt minus 2 I2z I1y cosine pi jt sine pi jt plus 2 I2y I1z sine pi jt cosine pi jt plus I1x sine squared pi jt. I use the fact that with these operators, it does not matter in which order they are written. And now, in a spectrum, we of course have both spins. So in a spectrum, usually we see I1x plus I2x. And so when we look at this, what do we see? We first look, for example, at this term, and then at this term. And we immediately see they are the same, just opposite sign. So kind of can neglect them. Then we have this term and this term, and it's the same. And what we're left with is I1x plus I2x times cosine square pi jt plus sine square pi jt. And if you know the formula, then it's clear what this is. This equals 1. So we really have just I1x plus I2x that remains. So nothing happens if you look at these two spins together. This is the strong coupling limit. That's the case of isochronous spins. For example, in a methyl group. And I think you all have learned at one point that a methyl group, it's just one single signal, although there are 3 spins. And that is this. Like you have these protons, and all the time you have transfer from one spin to the second spin, fourth and back, all the time. And from the other spin, the same, the other direction. But the sum of the two stays constant. And so although you have coupling evolution all the time, you will never be able to measure it. And that's if you have a signal that is not modulated at all, then you do not see a coupling. Then you just see a singlet, a straight line. The funny thing is, for the weak coupling evolution, here, the blue square, there you see our signal is cosine modulated. And the cosine modulated signal, that is always a split signal. It's cosine modulated by pi jt, meaning you will get a splitting of j. And that is why we see split signals in the case of weak coupling limit. In the case of strong coupling, you don't see anything. And you usually get taught that the couplings is the normal thing. Well, in nature, it's like this, that you have the isotropic coupling, and only because you, in addition, have the chemical shift term, you will see the splitting. So the natural thing of a coupling, if you would not have a chemical shift difference, then you would never see a splitting because of the coupling. But I should say something else. This is not true for dipolar couplings. For dipolar couplings, you always see a splitting because it's not an isotropic Hamiltonian. Yeah. And that's a funny thing. Like if you have a methyl group and you partially align this methyl group, then you see a triplet. From the two proton-proton couplings, dipolar couplings, to the other protons of the methyl group. So this is specific to J couplings and like this. With this, I would like to close what I want to say about the product operator formalism. There's tons of calculations that one can do and one should do. Very important ones. Most experiments used today are designed using such product operator formalism based calculations. But what this cannot do, we will see in the next part of the lecture, which is, for example, to characterize multi-pulse sequences where you want to have coupling evolution at the same time as seeing what is going on with pulses. So you see this is not possible. And that's why I also would like to continue now giving a very basic introduction into average Hamiltonian theory and what you may do with this. So where should we look for some new extension to theory? Let's say we have pulse sequence building block. And let's take a very simple example. Let's say we have a spin I and a spin S. And we simply have an echo, a heteronuclear spin echo. Now we can sit down and do every time the calculation, what is happening there. We can use the product operator formalism and calculate every time what's happening there. Or we just look at what this building block effectively does and then use that. Spin echo or Hahn echo, or for example, whatever inept is an example, or the perfect echo, and many more, where you simply use one result and then put it in to design a sequence. On the other hand, we also have multiple pulse sequences, typically shown like this, just a block. And examples are Toxi, decoupling, spin lock, EHH, Rosie, and in solid state, CP, and many more. Usually, when we look into the sequence, we see identical blocks which are cycled with some different phases. So I write, for example, a normal notation or frequently used notation is R, R bar, R bar, R, where R bar applied with a pulse phase phi is simply R phi plus 180 degrees. And this R bar, R, for example, is one version of the MLF4 supercycle. So this is super cycles. Yeah, for example, as I said, MLF 4, 8, 16, or XY 4, 8, 16 are two very common words. You have P5, M4, and many others, just to name some. And now, of course, in each of these elements here, when we look here in the so-called basic cycle, then we have pulses here, sometimes of different lengths and of different amplitudes. Well, I think you understand what I want to draw. And that is the so-called basic cycle, or the basic element, basic sequence of this. And that, for example, has the time tau b for the basic cycle. So such a multiple pulse sequence is very complicated, has several layers. And now we want to try to understand what this sequence does. And as we heard, it's not so straightforward to calculate it with something like the product operator formalism. We simply cannot do it. J evolution, as well as chemical shift evolution, as well as radio frequency pulses. So we will now look only at the basic cycle here. And what we then have, if we say uk is simply e to the minus I h k t k. So for example, this here is this is tk because this is the kth element of the pulse sequence, which has the Hamiltonian hk for time tk. If we say something like this, then we can write rho of tau b just equals uk times u2 u1 rho 0, and then u1 dagger u2 dagger times many others times uk dagger. And actually this is a very often used notation, and all the u's here are called the propagators. And it's just a different writing for this e to the minus iht that I already used throughout. But now, if we have this rho of tau b, etc., we of course can rewrite this as u effective rho 0 u effective dagger. You can multiply all these matrices, uk minus 1, etc., up to u1. You can multiply them. It's just matrix multiplications of quadratic matrices, so that's easily possible. And in the end, you get this effective propagator. And that has now all the information contained of this basic pulse sequence block. And if you need to apply this again, you simply take the propagator and only the effective propagator and do what you do. This is what I mean when I say what the overall pulse sequence does. You can write down in this one propagator. You do not have to calculate every step by every step, just once. And then you have all the properties, fixation properties, besides relative, of this pulse sequence element. That's easily done. There's only one slight problem with this. You can do this calculation exact only for a specific spin system. So you need to give it proton chemical shifts, for example, and then the coupling that is active. So you have one coupling, let's say 10 Hertz, etc. And then you calculate this effective propagator. And then you can do this and can apply it anytime again. But if the coupling now in your molecule is only 5 Hertz, you have to redo everything. Also, if instead of 2 spins, now you have a third spin bothering you, you need to do the calculation again. So that's also not really what you want to do when you want to characterize a pulse sequence. And there people came up with something they wanted to approximate now this U effective. We know this is e to the minus I h effective times tau b if we only look at the basic cycle. And now we want to approximate this with a simple to use Hamiltonian, simple to calculate Hamiltonian, and this is only an approximation, that this is e to the minus I h0 average tau b. So we now have something, this h0 average, that's the so-called average Hamiltonian to the 0th order. And where does this come from? Well, what you can do is you can expand H effective with the so-called Magnus expansion. And then you end up with something that you can write H0 bar plus H1 bar plus H2 bar plus higher order terms. And when you look at the individual components, then H0 bar is the integral of 1 over tau b from 0 to tau b of dt h of t. And h1 is minus I over 2 tau b times integral 0 to tau b dt integral 0 to t dt prime. And then we have h at the time t, commutator h of the time t prime. And for completeness, h, or not quite complete, but this is minus 1 over 6 tau b integral 0 to tau b dt integral 0 to t dt prime integral 0 to t prime dt double prime, and then commutator of h of t with h of t prime, commutator h of t double prime plus h of t, commutator h of t prime, commutator h of t double prime. And of course, higher order terms with even higher commutator terms. Luckily, if we restrict ourselves to some time period, this tau b, for example, here, we can get away already with a 0th order average Hamiltonian here, and that is what is typically used. In some exceptional cases, also the 1st order average Hamiltonian is used. I have not seen any case where the 2nd order average Hamiltonian has been used, but it's also possible, and even higher terms I don't think make any sense. Calculation will become too complicated. But let's simply restrict ourselves to the 0th order term. So this is the 0th order average Hamiltonian. And what does that mean? We have the integral, we sum up all the Hamiltonians and divide it by the time. That is simply really taking the average. We look, what's the average of this Hamiltonian? And of course, this neglects everything where we have commutators playing a really strong and active role. But turns out that this can be used quite nicely as long as we look, well, at the limitations. And a sufficient but not necessary condition for convergence of the 0th order Hamiltonian. Convergence meaning that the approximation is a very good approximation. That is usually given the integral of 0 to tau b of the norm of h of t dt should be less than 2 pi. So what does that mean? So for example, we have our hj weak, which is 2 pi j I1z I2z. There, the norm of hj weak is pi j, because the 2 is actually part of the operator. So because this is the case, we can calculate then pi jt must be less than 2 pi, and you can do the math yourself. We have then t must be less than 2 over j. And that's actually quite some time where this holds true, where the average Hamiltonian is valid. I mean, if we have a j coupling of 10 hertz, then 1 over j is 100 milliseconds. And so we have 200 milliseconds that we can calculate before we need to consider really strong deviations from theory, from exact calculations. On the other hand, there's a problem. For example, HRF X is, for example, sometimes minus, in liquid state, typically on protons, 25,000 hertz times I1x, 2 pi times, and when we do then the math, then this is clearly the norm of this HRF X is 2 pi times 25,000, and then our 2 pi 25,000 times t should be smaller than 2 pi, meaning tau should be smaller than 1 over 25,000 hertz, and that is 40 microseconds. So if we have a strong Hamiltonian present, for example, a hard pulse on protons, then we have a very, very short time where the convergence, the good approximation of this Hamiltonian is guaranteed. Now comes the second part that is always connected with average Hamiltonian theory, which is we want to separate the part of the Hamiltonian that interests us, which we want to have variable, from the rest. That means, for example, if you're interested in J evolution during a multiple pulse sequence, then we want to get rid of all the terms that are larger than our J coupling. Meaning we want to get rid also of the radio frequency pulses. Everything in the Hamiltonian, also the offset, we may want to eliminate. And this can be done using the toggling or also interaction frame. And so what is this now again? I think I best give you some picture here. When we are in the laboratory frame at a 1 gigahertz spectrometer, for example, then the Lama frequency of a proton is 1 gigahertz. That means it rotates with 1 gigahertz all the time. So when we pulse something, then also the pulse must rotate with 1 gigahertz. That means when we look at our pulse, so HP is for pulse. When we look at our pulses, then they are highly modulated with 1 gigahertz, for example. While the Zeeman term is constant all the time. It's 1 gigahertz. Just the spins rotate, but the Hamiltonian is constant. And the coupling here with the coupling Hamiltonian, HC, is also constant. That's even field independent. So what we do to eliminate this oscillation of the frequency here mathematically is we go into the rotating frame. And I expect that every one of you has heard of the rotating frame. It's like a carousel, and now we are rotating with 1 gigahertz, and then suddenly our pulse, that in reality in the lab frame is modulated with 1 gigahertz, stands still, is constant. That's a very nice trick. So you eliminate this modulation and you go here to constant pulses. At the same time, J-coupling is not affected, but the Zeeman term is very well affected. The Zeeman term, which is a huge term of 1 gigahertz, is being reduced here to the offset, so-called offset term, that is the difference frequency of a given spin relative to the irradiation frequency of our radio frequency field. So we have a very strong reduction of our Zeeman term. Now what we do is we go one step further. We take, for example, all so-called linear contributions to the Hamiltonian. Linear contributions, that is the radio frequency, it has only one term like I1x in the Hamiltonian, or I1y, or offset, which is the I1z term. And now we rotate our coordinate system with these linear terms. That means with the pulses and with the offset. We rotate ourselves all the time with the pulse. And then we eliminate the offset completely. Here, it's gone. And we eliminate all pulses. But then, of course, I mean, somehow the pulse sequence must come into play. Suddenly, our coupling terms get modulated. They were constant beforehand, and now suddenly they are modulated because we turn around all the time. And if we go now in this interaction frame, then we have the modulated coupling term, but there we can use the average Hamiltonian theory nicely because our coupling, let's say 10 Hertz, is the largest term in the Hamiltonian. We do not have to worry. We can apply average Hamiltonian theory for 200 milliseconds, which otherwise, if we would stay in the rotating frame, we would not be able to, only for 10 microseconds. We rotate in a way that the magnetization, no matter what pulse we apply, will stay at the same position that we started with in this interaction frame, not the rotating frame. It's also rotating, but it's not called like this. And so how can we see this? And there I would take a very simple example like the toggling or interaction frame. Let's assume we have a coordinate system, and I draw it like this for some reason. So this is X, Y, Z, and this is in the rotating frame. So our usual frame that we work in. Then we have here our magnetization. Our rho 0, for example, would be IZ, but we also have a Hamiltonian active that would be, for example, chemical shift Hamiltonian, which would be minus 2 pi nu I IZ. It's orienting along Z, everything else doesn't matter at the moment, but yeah. So now what we can do is we apply a minus 45-degree X pulse. Then we end up with again X rod, Y rod, Z rod as the coordinate system, and we end up with our magnetization being here, 45 degrees. However, our Hamiltonian, chemical shift Hamiltonian, is of course still along Z. Was a bit long. Now I can try to do this in the interaction frame. So the interaction frame then would start the very same way at the beginning of the sequence. Just now X int, Y int, Z int for interaction. We can have our spin here and our Hamiltonian as well. we apply the same minus 45-degree pulse, and then we certainly have our magnetization pointing the same way, Hamiltonian the same way as before. But now our coordinate system changed. Our coordinate system rotates with the pulse. So this is now z int, y int, and because it's a rotation around x, the x int stays the same. Our coordinate system rotated. And now, of course, we want to describe everything in our interaction frame. So what we actually want to do is keep our coordinate system constant. So here our spin, here our Hamiltonian, and we again this minus 45-degree x, we want this to stay the same. X int, y int, and z int. So what does that mean? That means now our magnetization stays along z, but z in our interaction frame. While the Hamiltonian can be found at plus 45 degrees around x, so the opposite direction. And that's the trick. And now what we do is simply we calculate an average Hamiltonian here using this interaction frame. And I think it's really best if we just do a very simple example. Then hopefully things become more clear. So let's look at the spin lock. Typically, you write it down like this, as L, and let's say along the y-axis. So in the rotating frame, spin lock is just a long pulse along the y-axis, constant amplitude for whatever, several milliseconds. And for simplicity, I restrict myself to a 360-degree rotation, which contains all the information. And then we kind of, I take my conventional coordinate system again. Now we don't have that much overlap. So 90y to so in all cases is x, y, z at the same position, 90y, 90y. And now I will draw again the magnetization, which is in the beginning, of course, along z. Then after 90 degrees, it is along x. Then it is along minus z. Then along minus x. And then we are along z again. This is simple and everyone should be able to follow. Now in the interaction frame, we can say that our magnetization is first along z, but it will always stay there. This we can draw simply because we're dealing with the interaction frame. But what does it mean now? The rotating frame coordinates and the interaction frame coordinates in the beginning are the same. And I will now draw the rotating frame. This is the rotating frame in the interaction frame, which I do not show here. So now, because of the 90-degree pulse, we need to rotate around minus 90 degree. So the y is still the same, but the x-axis of the rotating frame is pointing along z now, and the z-axis of the original rotating frame is now pointing along the new minus x-axis. And then we continue, so y is always the same. You can draw that already. And then we have x and z. Then we have x and z. And in the end, we are back again. Y does not change because Y is the axis around which we rotate. If we now look at, let's say, the chemical shift, H chemical shift, which is, of course, in the rotating frame always along Z, was here, and it was always here. Then in the interaction frame, it was along Z in the beginning, but then, of course, it always stays on Z. Now what we can do, we take the average Hamiltonian of the chemical shift, and we can see we have, let's say, 90 degrees is pi half, so I write pi half times omega I minus, and then we have in the toggling frame Iz minus Ix minus Iz plus Ix, and these are 4 terms, so we divide by 4, and the average of this, we can sum up, of course, is 0. And that's something that we know very well. If you apply a spin lock, the chemical shift is reduced to 0. It's not active anymore. But how is it now, for example, with J coupling? We, let's say, consider only the weak coupling case. Then it's also along Z. To distinguish it, I should draw it in different color. So we are along Z essentially. So we have, for example, 2 pi j, and we have again 4, so divided by 4. And then we have I1 Z, I2 Z. And in the beginning, we are along 1 and 2. Then at the next point, we have minus I1x minus I2x. In this second case, a single operator points along minus x in the interaction frame, but we have 2 terms now, and we assume that both spins behave the same. So they're both affected. So I need to multiply it, and minus times minus gives plus again. So this is actually effectively plus x, because we have 2 terms. It's a sum. And then we have minus I1z times minus I2z, and then we have plus I1x times I2x. So this negative one would also become positive. Here we would be in parallel again, and here also would be in parallel again with the others. So this time, the average Hamiltonian is not 0. Something remains, and we end up with pi j I1z, I2z plus I1x, I2x. And that is what you call a planar mixing Hamiltonian along the y-axis, with the y-axis as the principal axis. And when you look at it more closely, then we should see that this is pi j half times 2 I1z, I2z plus 2 I1x, I2z. So our initial Hamiltonian has been distributed over the x and y components. You have 100% distributed on 2 axes, so every axis feels 50% of the J coupling now. That's also known as the scaling of the coupling constant in such sequences. But in effect, it's a distribution. And I hope this shows you how effective this can be. So we know now for the spin lock block, chemical shift does not evolve. And we know we have a planar mixing Hamiltonian with the principal axis along y. You can directly write down the Hamiltonian and do whatever with it. And that's independent of the size of the J coupling or anything. This is a direct result of the average Hamiltonian theory combined with the interaction frame. Then maybe let's look at another example. And I have something prepared here. On the left-hand side, we see here delay, 180-degree pulse delay. And of course, only when we switch on the pulse, our IX or SX term, it's spins I and S for the two heteronuclear spins, the IX and the SX terms are constant and some value, it's a hard pulse during the time of the 180-degree pulse D. And before and after we have a delay, delta half. So this is a simple spin echo. Of course, also the chemical shift is active during the whole time. It's a natural evolution Hamiltonian, and that is proportional to the IZ and SZ term. They are also constant all the time. And then, of course, we have a coupling term, 2IZ, SZ. That's always also constant, at least in the rotating frame. Should maybe write this. This is the rotating frame. However, if we do this in the interaction frame, then what you see is that, of course, when you do not apply any pulse, it's equivalent. So here, 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 and here, we do not apply any pulse. And there it's the very same result as in the rotating frame. But then, of course, you apply a pulse. And although we usually apply a hard pulse, which is very short, we may be in a situation where we have a longer pulse, where it might happen that it becomes important. So we now have here what happens during the pulse. We apply an X pulse, so we get Z and Y components that are active during the pulse. That's what you see here. So the Z component here gets 0 and then gets negative, clearly because we follow the magnetization. On the other hand, the Y component rises until we are about at 90 degrees and then it decreases again. And now we look, what do coupling terms or bilinear operators do? And this is simply multiplying the Z terms with the Y terms of the individual spins. We assume that both spins feel the same pulse, and then it's simple multiplication. And so if the Y term looks like a sine wave for the duration pi, then what we see here for the coupling term 2IY/SY is actually a quadratic sine wave, sine squared. Then we also see this 2IY/SZ term. That is then cosine times sine in both cases. So these terms here have these waves, and the IZ/SZ term goes down like cosine squared. So now we know what is going on during the delay, including now the effect of the pulse. So we can try to calculate. First we see the IZ/SZ term. This is really 0. So there's no chemical shift evolving. That's really nice. The IY/SY term does not vanish. So what we effectively feel is in the interaction frame, like D half times I y. The duration d, and you see the integral is about half. So yeah, no, it's pi half, isn't it? It's the integral. If I remember correctly, here I'm really not sure at the moment. It's 2d over pi. It's a bit more than half. I think I'm correct here. Then the coupling term is 1/2. Then we have here d half 2IY/SY. Then the IZ/SZ term is, of course, delta plus d half 2IZ/SZ. And the other terms you see cancel out. And the result is not so surprising. At least for the coupling, we have here normal coupling evolution. And during the pulse, we have again planar mixing, this time with the principal axis along x, because it's this d half times yy plus zz terms. And this you will never be able to calculate with product operator formalism. But average Hamiltonian takes it into account, and then you can be more accurate in what you're calculating. And by the way, the y terms here for Iy and Sy, they lead to the phase factor. If you refocus it, you will see there is some phase shift that's offset dependent. Offset comes into play. And you also see here how you could get rid of this Iy or Sy term. That would be if you apply in the end another 180-degree pulse of duration d. Then we would have a negative curve, and we could eliminate this from a sequence. So we have this term here, and if you apply in the end here another 180-degree pulse, then the curve would become negative here, and it would be subtracted from each other. So this way we could get rid of this imperfection, showing you already that you can use pulses to correct imperfections of previous pulses. And that's one of the philosophy of either shape pulses or multi-part sequences that are usually computer optimized. When you do these calculations, like what I showed with the echo now, then of course you will modulate your signal. And you have to be careful that you do the modulation with small enough digitization. Just want to make you aware of this. This is one of the problems that one frequently encounters. Like the calculation down here with 162 increments, and you see that this is nice. That's the modulation that you would expect. But if you take 45 points, then you see already things are not that nice anymore. And if you drive it to the extreme here with a k equal 27, then really your average Hamiltonian will not be calculated properly. A general rule is that each time step that you calculate should result in, let's say, single-digit degrees of a rotation. So typically 3-4 degrees per digitization step. That's something that you're nowhere told. If you would like to do such a calculation, take care. So what we did here is 90 degrees steps and so on. It's not the usual way. It's only possible because there are no changes, and we can follow this in these big steps and get to the correct result. In reality, you would do only 3-4 degree steps over the whole 360 degrees, for example, for the spin lock, and then calculate everything. But of course, I want you now to do something, and I want you to try a highly used sequence. But I tell you, you can do it in an approximation, in an approximation, which leaves out the pulses. You know the nomenclature, just the line is a 90-degree pulse, the empty box is a 180-degree pulse, and we give it the phases x, y, 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 minus x, and the lower one is identical. And what I would like you to do now is drawing this sequence here the same way as we had the spin echo just beforehand. So draw this, how the x, y, and z component of the rotating frame in the interaction frame looks like. And then you can do all this. So yeah. You will use the pulses, and then you take just the evolution time. You can consider that the pulses are infinitely short. They will not contribute to the overall average Hamiltonian. So you can make your life significantly more simple, but the result will be, in essence, the important result that you get from this. And from that, you can really get the average Hamiltonian of this building block, and this building block is called the perfect echo. And this is heavily used in NMR spectroscopy. In essence, a variant of it is also the sensitivity enhancement, sensitivity improvement that you may have heard for HSQC experiments. And it is used in many, many cases. So it's worthwhile doing it. And yeah, have fun. So who could solve this problem? Was anywhere close? Okay. Maybe I show how I approached it. I'm sure there are even better ways. So we have the sequence up here. It's the same sequence on both spins. So in essence, we need to look only at one spin with the coordinate system. So if I go into the rotating frame, then simply red is the magnetization in the rotating frame. And you see from Z, it's going to minus Y, and it stays there and stays there and stays there. And then it's going back to Z. So far, I think everyone can do it. That's really nice. But then we need to do now the whole thing in the interaction frame. And actually, what I maybe did not explain well enough so far is that we now need to take the rotating frame and represent that in the interaction frame. So the violet frame here is always the interaction frame. That stays constant. And now we take the rotating frame here and the interaction frame. So when in the beginning we have X, Y, and Z component the same way as in the rotating frame, then after the first pulse, we do not rotate around the x-axis in the normal way, which would result in minus y. We would do it the opposite way, kind of a left-handed rotation, left-hand rule rotation. So we go the opposite way. So the z-axis actually will point now into the y direction in the interaction frame. And you see how it looks like here. Then what we need to consider now is we now have a 180-degree pulse around the y-axis. But the y-axis, of course, in the rotating frame, there it is a y pulse. It's always in the rotating frame, the axis of the pulse is defined. So it's a y pulse there. And so we now need to rotate around this y-axis. And in a 180-degree pulse, of course, it does not matter which direction. But remember, it would be left-handed. So around this y-axis, we will rotate the other way around. So yes, we go around the y-axis, so we have to have a rotation around this axis. Yes, it's around the y-axis. And that's where we end up the next one. And then we have a 90-degree pulse again around the y-axis. And you see, well, again here, it's around this axis. And then again, a 180-degree pulse here around this axis. And then we apply a minus x pulse in the end. So it should be this way. And then we end up in the state shown here in the end. This is not the same frame as in the beginning. You see, we have a phase shift in the XY plane, and that needs to be considered in the follow-up of the sequence. Like everything will be shifted by 90 degrees here in the XY plane, and that you need to notice and adjust the pulse sequence accordingly. But it does not have any effect on what we look at now, which is the Hamiltonian and how the Hamiltonians evolve. And for the Hamiltonians, I just drew the sequence again, just once, because we know it's the same on both nuclei. And now I look at where the magnetization is, and it's clear we have our Hamilton operator. And let's, for example, the IZ or SZ term, the chemical shift Hamiltonian would have the IZ and the SZ term. And so I started with IZ, SZ, and then it will be always kind of here along Z. It will always be along Z. I'm drawing it up here. We are pointing along Z, and now the Hamiltonian will always be along Z. We have to look along Z. So it is here, and directly after the 90-degree pulse, we are along IY. You see the Z in the rotating frame is Y in the interaction frame. So we're along Y. And there we stay for the whole duration of the delay. And then we have a very short Y pulse, and now the Z axis is along the minus Y axis. So we invert here. And again, we stay for this delay. Then we put a 90-degree Y pulse, and our Z-axis rotates to be along the X-axis. So we are now on the IX or SX operator. Stay there for quite some time for the delay. And then we have again a 180-degree pulse. You see already what happens. We are at minus X again till essentially the end of the sequence. Just the 90-degree pulse puts us back along Z with the Hamiltonian. So this is nice, and we see directly chemical shift, which contains IZ and SZ as the main operators, will be vanished out to zero. So no chemical shift will be active in this, which of course you see already right away because we have two spin echoes, so that's nothing really new. But now we take these components and of course, when we then have a coupling Hamiltonian, 2 pi j I z times s z is the Hamiltonian. So it's also along z in the rotating frame. It moves the very same way, the individual operators as shown here in red. And now we simply multiply one spin with the other spin, the I spin and the S spin. They all move the very same way. So it's very easy. You just multiply this by itself. This here is kind of 1, and it stays 1. But this one is minus 1. Minus 1 times minus 1 gives plus 1. Then you're along X. 1 times 1 gives 1. But here, minus 1 times minus 1 gives 1 again. So you stay here. And you see right away what happens. So in this interaction frame, the Z term of the original Hamiltonian suddenly ends up in an XX and an YY term. And you can write it down like this. The average Hamiltonian here for the weak coupling limit is 2 pi j divided by 2, because it's only half of the sequence time. And then IX SX plus IY SY. And that is a planar mixing Hamiltonian with the principal axis around, the Z being the Z axis. And that's a very useful element. It is spin state conserving in the X and Y dimension. It can be used as a Toxie element. It can be used in all kinds of things, for example, sensitivity enhancement, for example, replacement for heteronuclear Hartmann-Hahn even, etc. So you can do a lot of things with this element, and you just need to know what is the average Hamiltonian here to really know what to do with it and be creative. So this is a very powerful method, I think, and well, with this, I think I close down the spin density operator formalism, product operator, as well as now the average Hamiltonian theory. And well, in the next section, we will deal more with how to describe a system where you also want to deal with relaxation.